Welcome to Module 48 on sequence modeling and vanilla recurrent neural networks, or RNNs. So by the end of this module, you ought to be able to identify the types of tasks that require, or at least could benefit from, sequence modeling, and explain why the kinds of feed-forward networks, the multi-layer perceptrons that we've been using, might be poorly suited to them. You should be able to describe the basic vanilla RNN architecture. It's a little bit of its recurrence equations, how it shares weights, and so on. You should be able to trace a forward pass through an unrolled RNN for a very short sequence. You should be able to explain backpropagation through time, or BPTT, at least conceptually, but also to some level the calculus. It's going to reuse a lot of the same ideas we saw previously when we talked about gradients and deep neural networks. And then we're going to give you the tools to implement an RNN using PyTorch and apply it to sequence tasks. So sequence data is extremely important. This is how I kind of got into machine learning generally. I started working in natural language processing, or computational linguistics, as it was once called. And it's a sequence. So the words that we produce in a sentence, order matters. Words in a sentence makes sense, but A in words sentence might not make as much sense, right? So the order of events matters greatly. And if you're doing language-based tasks, then you have a variety of things you might want to do with it. Only two of hundreds of possible examples might be simple next word prediction, which lie at the feet of a lot of modern transformer-based large language models. You could take text and try to just identify the sentiment of that text. Is the writer happy? Are they sad? Are they stressed? So doing classification from a sequence. Audio and language are often related, and so in fact I got into speech recognition in the early days. And speech is also broken into a series of frames, short little 16 millisecond sections of speech, all laid out in time, and then changes occur over time. And then from that we can do speech recognition. We can get whole transcripts, word level transcriptions of what was said. We can get phoneme-based transcriptions, so they're the parts of auditory speech. We can do tasks for general time series. So given temperature readings and maybe some other data over time, air pressure and so on, we can make predictions about tomorrow's forecast in a sort of regression task. Biology also uses sequences, so nucleotides in a genome sequence, by its definition, the sequence matters, order matters. So you may want to learn something about protein function in a biological context. And then finance. So you've probably seen stock markets over time. You might want to predict something about a particular stock given historical changes, again, in which the sequence, the order matters. So all of these possible domains use sequences. Some of the key differences from the kind of data we've seen before, so-called tabular data. So in tabular data, all of the rows, all of the individual data points were IID. So you could just shuffle the data points without changing the task. In fact, sometimes we needed to shuffle things to do, as a pre-processing step towards k-fold cross-validation, for example. But regardless, all the data was meant to be sampled independently from some underlying distribution. But now, the order itself carries information. The the adjacency of nearby measurements matters. Long-term changes matter. So any kind of shuffling will destroy meaning. So that is to say that a sequence model must use the history of what has been seen in the past as a build-up or a lead-up to the current moment in time to make sensible output at the time step you're at. There's a couple of different taxonomies for how we might think of a recurrent neural network. So here we have steps in time going from left to right. So we have multiple observations. We have big T time steps. And so for the case of sentiment analysis, for example, you'll read one word at a time. Each of these X's will represent one word in a sequence, and you'll feed them into a neural network. You'll have some representation we're calling H for now. We'll just define it soon. And that representation for the meaning of the sentence will gradually change over time. So by the time you've read the third word, you want to incorporate information from that third word, which is this black arrow, but you also want to incorporate information from everything you've read so far, which has been sort of encapsulated or compressed into this tight little representation, H2. So the representation of what you've read previously, H2, plus the current word gives you the representation of everything you've read up to and including the current word. After you've read everything, over time you've read big T tokens, then you can make your prediction. Y is happy, sad, angry, frustrated, whatever the sentiment might be. I want to mention that I flipped the order of these graphs. So sometimes, usually, I like it when the inputs are at the bottom and the outputs are at the top. But for convention and for some other reasons, we're just going the opposite direction. But it should be obvious to you what's going on. One-to-many is almost the opposite. Like in this case, X might be an entire image. So maybe I have an entire image and I represent it somehow. Maybe I use a convolutional neural network initially to get an initial representation of my input, H sub 0. So H sub 0 is some hidden layer of a convolutional neural network. And then I gradually unpack it, and I'm going to print out word by word a caption for that image. H sub 1 is the first word. H sub 1 is the representation of the image, minus the fact that I'm going to write Y sub 1 out to the output. That's my first word of output. And then H sub 2 says, well, I've written something out previously. I'm going to write Y sub 2 out now. H sub 2 kind of encapsulates that hidden information. And then gradually you'll keep on writing one word at a time in these outputs Ys until finally Y sub S will be the final output. It could be an end of sequence token that you output saying that you're finished writing the caption for this particular image. I'll mention many-to-many now briefly. Actually, I'll start with many-to-many synced for now. So this is what we're going to be mostly looking at in this particular short module. In this one, we'll have, for every moment in time, a particular input and a particular output. There's lots of uses of this particular kind of model. This, again, follows the same kind of idea as this first many-to-one model from a few moments ago. The only difference is we're not going to wait until the end to make some kind of determination. We're going to label every single frame that we have. So POS stands for part of speech tagging. This is a classic natural language processing task. A part of speech is something like noun, verb, gerund verb, past participle, adjective, etc., etc. And sometimes it's helpful to do downstream processing in language to say that this instance of the word chair is a noun, which is something you sit in, or it's a person's title, versus it's a verb, which you could chair a meeting, and sometimes it's useful to know the difference between those things. So given the word chair, you give it the part of speech tag, Y sub whatever would be verb, right? So you're going to tag every single input that you have. And then the hidden representation will kind of continuously keep sort of an packed internal representation somehow of everything we've done previously in time. So it remembers what happened in the past. Finally, many-to-many. We might come back to this in the next module. I haven't decided yet, but in this case, we're going to read up a input sequence like we did in this many-to-one instance initially. And at the end of that, we're going to have a representation. Previously, I called it H sub t. Now I'm calling it C, which, this often a little bit of extra complication happens in here, but basically this is a representation for the entire input sequence. So C represents everything in the order that it came in. And then I want to unpack it word by word, more or less in the same way that I did in the one-to-many example. So many-to-many with an offset is kind of many-to-one, followed by a one-to-many. This is often called seek-to-seek for sequence-to-sequence, because I have an input sequence, I have an output sequence. These sequences can be of different lengths, so T and S don't have to be the same length. And more commonly in machine learning, this is called an encoder-decoder model. So first I encode information in my input sequence, and then I decode it one by one. And then the common canonical use case here is machine translation. So as input, I get big T words in a source language, like in an English language. I have big T English words, and then I want to translate it to big S French words, or vice versa. So I encapsulate the meaning of the English sentence, and then I decode it one word at a time and print out the appropriate French words in the right sequence. So we're gonna focus mostly on this many-to-one model because it's simple, and the many-to-many synced one because it's also simple. So here's again a little anti-example, coming unstuck in time. Anyone who recognizes the reference to what coming unstuck in time means would get bonus points if it was ethical for me to do so. Is this a great author came up with this term? Anyway, you have sentences. All of them are 50 words or less, and you want to, for each of these sentences, classify the sentiment of those sentences. So this sentence was happy, this sentence was sad, etc., etc. So the naive approach would be that you would get the word vectors for each of these words. We talked about word vectors in the past when we were doing word embeddings in the context of representation. Remember we had the, like for a given word, you train a neural network, you pull out one of the hidden layers, and you can potentially project it down, and then we had these clouds of words in space, and they encoded all kinds of useful, meaningful semantic information about those words. So every word had a vector that represented it, of numbers, and you could concatenate those together in the sequence that the words occur in, and pass all of this into a good old-fashioned multi-layer perceptron. What are some problems? The first problem is, well, you have a fixed input size. MLP always has to take the same number of inputs. So what we can do is, well, we could pad short sentences with fewer than 50 words with like 0 vectors. It's possible that eventually you want to keep on using this model and suddenly you get a sentence with 52 words in it, for example. Then you'd have to trim off like some of these words or filter some of these words out, which comes with its own problems or challenges. So like, what is the right thing to do? This all seems kind of hacky. And not in a good way. Hacks can be really great, but this hack is not necessarily great. Position encoding is lost. So when you learn, when a particular word occurs in, say, position 3, like for argument's sake, and you want to learn something about the meaning of this word in its context, and imagine the context would occur in another sentence now in position 30. Each of those words in the multi-layer perceptron will have different sections of the weights that have to be learned through backpropagation, and would have to learn the same thing twice. So the same exact context, or the same exact words, early in a sentence and late in a sentence, we have to learn those things individually. Like the meaning of the word "same" would change based on when it occurred in a sentence. I mean, probably the next module we'll see how sometimes that is something we want to encode, and sometimes a context can change the nature of a word over the course of a sentence. But generally, like we're wasting time. Like we have to learn the meaning of a word in every position that it could possibly occur in, and we may not have data for that word occurring in all the possible contexts and all the possible positions it can occur in. So that doesn't make any sense. We're not generalizing well. That's even worse than the fixed input size hack we have to deal with. And then, just practically, for sequences of length t, we have feature dimension d. So we have like d-dimensional vectors representing our words. Now imagine that we want to, like 50 is not enough. We want to read paragraphs or small documents. So now we have to use a model with 100 words of context. If you double, or of the window size, if you double the size of the window, t, then you're going to double the size of the parameters, and this doesn't scale very well, all right? So yeah, a feed-forward network will have no memory, no positional invariance, it won't like for any kind of real-world scenario using real data. The kind of models we've been using is not going to scale very well. So let's talk about vanilla RNNs. When I say vanilla, I mean basic, not the plant, not the flavor. So a recurrent neural network, or an RNN, has a hidden state, h sub t, that will be updated at every time step t. So here is h sub t, here is this function, and we have these three terms. The second and third term is basically a representation of what we saw previously with inputs x, passed through this weight matrix. So we have a weight matrix, which we can learn using the techniques we already know how. This is an x by h matrix, where we have like the size of the input vector x and the number of hidden neurons, small h. So we learn this matrix like we know how to do now. We have the input at time t. We also have a bias, like we often do. Also, every layer is going to have these biases into the hidden layer. So we've seen these two terms together already. But now we have this extra term. This extra term is a function of the hidden vector back into itself. This is where the recurrence comes in. So we have the hidden vector at time t minus 1 when we read the t minus 1th word, or we saw the whatever the input was at time t, whatever x sub t was. And then we want to learn a relationship describing the change of time from one moment to the next, which will be encapsulated in this weight matrix WHH. So there's H elements or neurons in the hidden vector. So it's a little square matrix that tells you how the neurons of those of the hidden vector should change over time, and encapsulate changes in time. And then finally, at the very end, in a model which is many-to-many and synced, we're also going to be passing outputs. In fact, if you have layers and layers of these recurrences happening, then every hidden layer is going to pass like an output or an activation up through the neural network. Nothing really changes here. We still have our hidden layer. We still have another weight matrix from the hidden layer to whatever the output dimension is. This could be another hidden layer above us. We still have our bias term, b sub y. And then this is y sub t, which can be passed into a nonlinearity. Okay, so we've defined this already, but I just wanted to write it out again because it's been a while. Some crucial things. Regardless of the time steps, the relationship between inputs and the hidden vector are going to be shared across time steps. So whenever I see a particular input, whatever time t it is, I'm going to learn something about it. So this matrix is going to be shared across time steps. Same goes for w sub hy. And also WHH. So like as I'm learning these weight matrices and learning how to optimize them, eventually I'm going to learn something helpful in this weight matrix that's going to let me remember information as we move forward in time. It will also allow me to learn the dynamics of what my inputs and outputs are related to the hidden layer. So if I decide to make a particular output at this particular moment in time, that's when I kind of unpack information like we saw a moment ago in the decoder part of the network. So I wanted to visualize this a little bit. This is often the kind of slide I put at the beginning, not at this point, just to make sure we're all on the same page. I think we already are at this point. You're all very clever. Here on the left is how I viewed it a moment ago. We have a bunch of inputs. We have outputs at every moment in time, and we have a hidden layer, with a hidden representation at every moment in time. Can move over. There you go. Pardon me. But often the way we're introduced to it is like this kind of form. We have like inputs like given at a particular moment in time, x sub t. So this is the input at a time t. We have an output at time t. And then we have a hidden layer that feeds back to itself. And this is kind of how I saw it initially. These two visualizations mean the same thing. We still have a weight matrices that are going to be learned between x and h, another weight matrix between h and y, and then we're going to have a third weight matrix which is sort of h back into itself. Here it's shown by this little kind of curved graph, which I struggled to draw properly. I still haven't really. But this weight matrix, this kind of recurrent aspect to it, is the same weight matrix that we see here in these green arrows that go from left to right. Each of these little boxes, for right now, they're just like, you can think of it as a hidden layer of neurons, and the same weights will be applied at every point. So unrolling in time, taking this neural network with a small number of weight matrices, but then unrolling it to a large sequence in a particular observation, you're going to have a sequence in your training data, and you're going to have an error signal, either for every single output or at the end of a sequence. Especially in the latter case, but even here, when you have an error at time 4, right, for example, and you make a mistake or you have a loss on this particular output, you're going to have to explain that loss. You're going to have to use gradients to push the error or the loss back through the neural network. And if you follow the computational graph back through this neural network, you follow these arrows backwards, you're going to have to change the weight matrix from y to h, but also from h into itself. And h into itself has changed kind of many times, like the actual values I've obtained as I got to time equals 4 is different over these moments in time. So you're going to have to kind of unroll this neural network over all of these steps. So the gradient's going to have to be pushed back through this neural network, which already is pretty deep, I have all these hidden layers that stack on top of each other. So as you can see, like even though I have a pretty simple looking neural network on the right, which is how you might conceive of it in terms of memory, in terms of actual inference and inference during training, we get very deep neural networks indeed because of all of these unrollings. So we're going to have a lot of depth to have to contend with. We're going to have a sequence T. If T is big, if T is 100, we effectively have a 100 layer neural network with weights that are all tied to each other. So this is very similar to the kinds of problems we saw with gradients in modules 33 and 34. And we'll talk about this in a moment. So I want to talk about backpropagation through time. So training an RNN means sort of minimizing the loss over the whole sequence, not just the loss at a particular moment in time, but like here's our neural network. We have to minimize the loss over the whole sequence. So in many to one, when we have a sequence in and then we have one output out, like a classification for the entire sequence, our loss can be just, the output at time big T was this. The desired output was that. We can compare these two things against each other. We can use the cross entropy loss if this is a classification task. The binary cross entropy if it's a binary cross classification task. If it's many to many, then we're going to have a output at every point in time. That's y sub t hat. We're going to have the desired output at every time. That's y sub t. This is a supervised training task. There's going to be a difference between these two things encapsulated within this loss. And we're going to have a different loss for every single moment in time because we're doing many to many. So we're going to have big T losses for each output. So we accumulate all these losses, and then we just kind of take the average of these, which is like time series forecasting, for example. So backpropagation through time is basically just good old-fashioned backpropagation. We're actually not doing anything that fancy now. It's just that we've unrolled the entire graph, and then we're going to do backpropagation through all of it. The forward pass, when we're doing the inference and getting our predictions, we're going to compute all of our h sub t for every moment t, and every prediction t from t equals 1 to the end. And again, for a many to one, this might be only one output y sub big T. We'll compute the loss. This can be like in either of these scenarios. We have a couple of different possibilities. And then we do our backwards pass. We want to compute the derivative of the loss, big fancy L, with regards to the hidden layer at time t, h sub t. And we have to do this backwards from t being big T all the way to t equals 1. Again, because we're dealing with a neural network that looks like this. This is our computational graph, so we basically follow the same steps that we took previously in this class. So the key gradient equation, again, is the chain rule. So again, this is nothing new is happening here that we haven't seen already. We have some function of the derivative of the loss with regards to the hidden layer at the very first moment in time. This is unrolling all the way to the beginning. And because of the chain rule, we can break this down. This is the loss with regards to the hidden layer at time big T times the derivative of the hidden layer at time big T with regards to the hidden layer at time 1. Okay, so we started unrolling this, but this first factor over here, this one right there, is also pretty complicated. There's a lot of intervening steps between big T and 1. So as you've already seen, I can kind of apply the chain rule over and over again, iteratively, all the way down the line, so that what I get is just a big product of all of these differentials, of the all through the computational graph. So nothing new is happening here. I just take the product of at any time t of the hidden layer at time t with regards to the hidden layer at time t minus 1. Okay. So again, identical form that we saw previously. So if you got it before, you get it now. If you didn't get it before, maybe reinforcing it now will help you get it. And if you still don't get it, it's always, my door's always open, so to speak. But regardless, we have this big gradient, and we've broken it up very simply into just a sequence of multiplications. So these derivatives are stored in these matrices called Jacobians, which we're just kind of skirting over kind of superficially in this course to a large extent. But because of these Jacobians and because of their norms, and so it's a measure of their magnitude, of their size, we can still end up with vanishing exploding gradients, right? So The same exact problem that occurred with deep neural networks generally occur here also, because unrolling over time results in big deep networks. Lots of products, and these products are very small. The product of very small numbers close to zero will go to zero, and then they vanish, and then we don't learn anything, and all those problems still exist here. So each Jacobian, this is a bit of a stretch, a bit of an aside, but it's still useful to know. So each Jacobian factor looks like this. It's the weight matrix of the derivative of hidden layer at time t with regards to the hidden layer at time t minus 1 is like the diagonal of this f function, like the diagonal of the derivative of this f function we defined a moment ago, times the weight matrices. So here f prime can be, say, 1 minus tan h squared if we're using this function, and it's going to be somewhere on 0 to 1. So, I mean, again, this is a stretch. I don't expect you to memorize this part of it, but you can take it as read for now. So if you have big T steps, the product we saw before is going to have t minus 1 factors like this, and the spectral radius of the weight matrix W sub HH will control the behavior. So I'm calling it rho here. These are basically just the norms from before. If the norms are very small, then the gradient vanishes, and then the early steps, like whatever happens early in the sequence, won't help me learn anything. If my norms are very big, the gradient will explode, and then training will jump all over the place, and it'll be very chaotic. And what we want is our norms to be close to 1, so that everything's stable, and then we can push everything backwards. This is hard to achieve in practice with just vanilla 10H activations. We saw previously how it can be hard with other kinds of activations. We also saw mitigations against it to help normalize at layers. So think about that a little bit. So in practice, gradients, will eventually fall into one of these traps. Like the more steps you have, the more likely you are to end up with a norm that's going to be super big or super small, and any kind of normalization notwithstanding. Truncated BPTT, this is a side note on a side note, but sometimes what they do is they take these small little steps. They only take k equals 20 steps at a time, backwards in time. So you take these gradients over these small little windows and then compute them periodically. Sometimes these windows can move, so this 20 steps in time can change over time. But this limits the amount of memory you need to have to compute all of these big gradient matrices. It can help speed things up a little bit. It helps stabilize training because you only kind of have these little silos where you don't have to multiply a tremendous number of potentially very small numbers together. You only have a limited amount, so in some sense vanishing becomes less of a problem. And also even the exploding gradients can be contained within these little silos. I can maybe add a citation here. I can send it on the Teams link, but helpful to know anyway. But just mentioning these kind of truncated ideas, amongst others, help motivate the idea for gated architectures. So in Module 49, we get to a form of neural network, which is sort of an extension on the kind of RNNs we're talking about in this module. So let's get to the actual worked examples to see how this works in practice. So a common mistake, if you wanted to experiment with RNNs versus good old-fashioned MLPs, what is fair? You always want to do experiments in the most fair way possible. You don't want to give an undue advantage to one model or the other. And in this case, you might be tempted to say, well, our baseline now is our MLP, the old-fashioned feed-forward neural network, and it's very limited given its time horizon. And all the problems we saw earlier, MLPs are not good at sequences, so we're only going to have sequences of fixed defined lengths. Like every input has to have 5 observations coming in a row. And if that's the case, then we can do a direct apples-to-apples comparison of MLP and RNNs, and we might pat ourselves in the back and say that we're doing good science. And like my approach is usually to try it anyway if you have the time, because why not? You're going to see some interesting phenomena. Unfortunately, this is not necessarily fair. In this particular case, we have a whole new architecture, RNNs, which are designed to kind of memorize something about change over time, or at least incorporate how things have changed over an entire sequence. And they're flexible. You can pass sequences of length 1, you can pass sequences of length 100, and the model will flexibly accommodate either of these. So this kind of limited scenario I mentioned a moment ago will be too restrictive, and through trying to be fair, you have actually been very unfair to RNNs, right? You've kind of tied its legs together in a race, so to speak. You don't want to do that. We're not going to do that. We're going to pass a sequence that information is going to eventually fall out of the window in which we'd expect the baseline to have good knowledge. So this is a very toy example. We're going to have a random walk sequence of length t equals 30, and then our goal in this toy example is simply to recover the starting value. You can come up, with a real-world example of how you might do this in the real world, but like where did we start this walk from is the classification task. Our x sub 0, our first point in this random walk, is going to be drawn uniformly from 0 to 1. This is the unknown seed. And then we're going to have this nice sort of control theoretic walk. So our position at time t will be the position at time t minus 1 plus a little bit of noise epsilon sampled from the noise, the Gaussian distribution, with mean 0 and variance 0.05 squared. And again, all we want to do is predict what x sub 0 was given like the view at the end of the sequence. This is going to be hard for MLP, or at least it should be. We'll see what happens. So the MLP will only have access to where we're going to set it up to the last 5 steps. And so we'll have a short recent window, so we'll have some context, but it'll be unordered to some extent. Well, it'll be it won't have like an explicit notion of change in time. Any kind of order will be encapsulated simply within the nature of which order the inputs are in. There will be 25 drift steps, so this window will basically carry almost no information about x sub 0. Therefore, given the setup, the theoretical lower bound on the mean squared error for the MLP using only this little window should be approximately 25 times sigma squared. Like, if you don't know why, you can just trust me, it doesn't really matter, but this is the theoretical floor for the performance of the MLP. The RNN will see every step from x sub 0 onwards, so and can somehow store x sub 0 in h1 and then remember it and pass it forward in time. So the h vector, if we do a good job in training, will keep on remembering what x sub 0 was. Every moment in time, it will always keep on reminding itself what x sub 0 was. There is some noise, and this noise is going to be proportional to sigma squared, so RNN will have a much lower theoretical bound. There's a whole section of machine learning work that just focuses on theoretical bounds here. We're just getting a glimpse of it here in this toy example, but here we are. So theoretically, RNNs should perform better, but we'll see what happens. The proof of the pudding is in the eating. We have to do the experiments. So we generate some data. Here's how we do it. I'm not going to get into this. You can read it yourself. I always feel tempted to. Anyway, so this is the starting positions over here. These are our x sub 0s. And then at every time step, we're going to add some noise and then gradually walk around, and then we end up here at the end here at time t equals 30. Okay, nothing fancy. So the MLP window is almost by definition blind to the seed. So by the end of this particular sequence, we started here at x sub 0 being around 0.54, it looks like. We've taken all these walks. These are all the positions of x sub t at time t over time. The MLP will have as its input 5, like a window of 5 always. So it'll see time 25, 26, 27, 28, 29, and 30. I guess that's 6. I'm 5 plus 1. 5, 6, 7, 8, 9. Yeah. What information will be available given the window position? This graph is also not too important for the empiricism of what we're about to do. But we have the per step noise floor, which is sigma squared over here. So this is like the floor of knowledge. This is sort of the background radiation of this fictional universe, the noise of it, sigma squared. The MLP lookback is 5 steps. So the steps from the end of the sequence is kind of encapsulated here by this kind of orange line. And at every step, like we could have been storing some information, or we're accumulating information at every time step, but we have a cutoff over here, and we only have a certain amount of information here. And when I say information, this is really in the form of the theoretical lower bound. So this isn't like information theory, like entropy information, which is a fantastic other field here. This is basically like what is the worst we can do if the beginning of the sequence was within our time window, and if we had bigger and bigger sequence windows, we could store more and more information, but we don't, so we can't. So this is all very theoretical at this moment, but it emphasizes, like, given this little shaded region, the MLP only has access to a very small history in the recent past. So let's define our RNN and MLP. So again, we're going to use CUDA. We're going to use our data loader. Nothing fancy here. Our MLP, we're going to use batch sizes again, like we did in previous modules. Two little classes. Our vanilla RNN is going to be just, like we're going to initialize it. It's going to have one hidden layer. Its hidden size is going to be 64, set arbitrarily as a hyperparameter. The nonlinearity in this case is going to be tan h. Again, you can go around and experiment with this, try different nonlinearities, see what happens. We have one hidden layer here, this RNN, and it's going to have this output, which is a linear output. Again, we talked about this in the context of CNNs. You have a complicated neural network, you put a little head on it, a linear neural network, and it's from there that we're going to do regression or classification predictions. This is our RNN, and we're doing a forward pass. We pass the input through the RNN, and then we take that output, pass it through the head, and then that's going to be the output from our forward pass. So an RNN, the RNN, I'm cutting corners here a little bit. Somewhere back here, I called torch.nn, and I'm using that, like torch.nn, to just say use an RNN. So torch has a neural network sublibrary, and RNN is one of the objects in it. The MLP baseline is a sequence like we saw previously. It's a layer with ReLU, a linear layer with ReLU, and then linear. So we're trying to match up the parameter sizes a little bit. So you've seen this kind of class before. We make our vanilla RNN using that class, hidden size 64, send it to device. MLP baseline, hidden size 64, send it to device. We have our naive baseline, so predict the mean of whatever the training seeds are. So this is our super simple baseline. So there it is. And let's close this up. So nothing really too new is happening here other than the fact that we're using the RNN function / class from Torch. And just to emphasize, we're still using linear heads on top of it. I'm printing up the number of parameters, so the RNN has about 300 fewer parameters than our old-fashioned MLP baseline, so it's around the same order of parameterization. We have our naive prediction MSE. This is 0.08. And we still have our theoretical MLP floor. So here we go for training. Nothing much is happening here. Like, again, I'm going to ask you to go through it yourself. The code is provided to you to play with, but training the model is pretty much following the same sequence that we did before. We take our input and output data, X's and B's. These are our batches from, in every epoch, we have our batches, which we get from the train loader. We pass this data to the device, so we can do all our nice matrix stuff. We zero out our grads. We compute our losses. We compute the backwards function. We're doing norm clip, grad normalization here. We do our optimization step. Our optimizer is defined up here. We're still using Atom, given a learning rate, it's nothing new. And then we get our evaluation, like we have many times before in this course. So you'll follow along. Now the big reveal. Here is like the outputs of the kind that we tend to always put out. We're just doing a plot over time of our loss and our evaluation during the training phase. So we have our MLP theoretical floor. So how bad can the MLP do theoretically? That's this orange line over here. We have the noise floor, like how bad can we do because of the inherent randomness of the universe? That's this green line down here. This is scaled on the log scale. I don't know why 10 minus 1 didn't show up here. It did for me a moment ago, but this is a log scale just to kind of emphasize things a little bit. So keep that in mind. Oops, come on, Linux. I have a little script that lets me fix this hardware problem. Anyway, you can see the RNN MSE on the log scale for training. Sorry, I'm going to start with the MLP first. The MLP for training and validation, these dashed green and red lines respectively, end up kind of plateauing very early, way up here. So the MSE, the mean squared error, is really, it looks fine, but compared to the RNN, it's relatively high. The solid blue is our training MSE over the epochs of training, and the solid orange is our validation MSE over the epochs of training. And both of them drop below the theoretical minimum of our MLP. So we're doing better than the MLP ever possibly could, theoretically. We're also empirically doing far better. You can see the big difference between our feed-forward MLP and our RNN that can remember backwards in time more than 5 steps. So everything's working out great. You also, I'm not sure if I'm going to ask you, I can't remember if I've asked you this. Maybe I'll ask you now, and I won't explicitly tell you. Hopefully, not on the next slide either. Look at the curves for training and validation. Look how close they are to each other. Is this an indication that the RNN is overfitting or underfitting or something else? Think about that a little bit and try to come up with an answer you're comfortable with. But regardless, both of those curves are way better than the MLP. So a big win for RNNs. So in summary, the RNN sees all 30 steps in some sense. Like it reads everything in, and the input at time x equals 0 or 1 is in the hidden layer, and then the hidden layer kind of propagates through every step in time until the very last moment where it can make its prediction of what x sub 0 was. It ends up with a final validation MSE of 0.013 or so. The MLP is, an order of magnitude or more, depending on what your magnitude is, worse, because it can only see the last 5 steps. And predicting the mean, will see nothing. It's using only priors and is worse than either. So MLPs are still better than not having an MLP, but RNNs did great. So they lived up to the hype so far. So the fact that MLP kind of seems to fail here is not because we trained inappropriately or we set the hyperparameters wrong. If we maybe changed if we change the context, the width of the hidden layer from 64 to something else, would that change? No. There's an information theoretical limit to what it can learn, because of the size of its input, right? And if anything falls out of it, then it's going to forget it immediately. It has severe, I guess it's retrograde amnesia, so it's not going to do a good job. But the RNN wins by design. Its hidden state h sub 1 will receive x sub 0, and then it can memorize it. And it'll learn to memorize it automatically without having to be explicitly told, which is another fantastic outcome of neural networks. And here I am again. Sorry, I can't tell when this camera zooms in on me. It's like it's zooming in. Like I'm not sure if it zoomed in for some dramatic effect when I revealed how great RNNs were doing or not, but it should have. So yeah, this is great. We have memory now. So we have RNNs with memory, which is another thing that we know animals have. And if neural networks are biologically inspired, then now we have at least a very crude representation thereof. Another worked example. So RNNs are very useful in the field of natural language processing. We're going to use a simple recurrent neural network over words now to classify short news headlines and their blurbs into topics. So either this blurb is like from a news source is world, sports, business tech, or sci-tech. So there we go. This will be like a nice, I think there's a bit of a syntax error here. It's not a big one. This RNN will see real text as real data, not toy. We're going to build a compact representation of actual text. So we're going to actually be doing not just looking at something that's control theoretic, but something real life from real data. And we're going to see if we can achieve high test accuracy. This is yet to be seen. Always do the experiment. So this is a public data set, and Torch Text, which is yet another library you have to pip install in your Conda environment. There's AgNews, which is used for a lot of baseline experiments like this one. It already comes with training and test predefined for us. It says 120,000 training samples and 7,600 test samples. And each of these has like text as input, actual text, and then the labels from these 4 categories as output. We're going to take a small subset just for this demo. Again, these slides are essentially Jupyter notebooks, and it took a long time to rerun them every single time. And we're going to do a little validation and test set experiment. So here's we're going to be doing subsampling, 20,000 train, 5,000 validation and test. And here's just a representation thereof. We're going to use the word tensors quite a lot. Tensors are, you can think of them as matrices for now. Matrices that represent something in our data. There's another small syntax thing. This should be smaller, but it's not a big deal. We are going to trade accuracy. So the results of what I'm going to show you is going to be not as good as I can. It's one of the drawbacks of doing it this way. We're not doing a full big experiment here. This is just for the purposes of the slides and the video. When you get this code, you can go ahead and skip this step and not subsample and see how well you could do without the constraints of having to make slides. So often, this is a bit of a side note, like this is not a natural language processing course, but often you're given the actual text and you have to convert that text into the numerical representations. The BERT model is still sometimes used. It's an old transformer-based neural network that has a neural network that understands time in a way that I'll talk about later in another module. And it also represents words and subword units as representations of numbers. Sorry, here we are again. This is not Linux's fault. This is the hardware manufacturer's fault that it keeps on zooming in. I want to make that absolutely clear. Usually we have to do all the work of building a vocabulary, mapping words to integer representations, truncating, padding, and all this sort of thing. But this is done automatically for us. So we already have these tensor representations. We just have to keep them. But if in other data sets, we might have to do a lot of extra NLP kind of work, which is beyond the scope of this particular class. We already have the tensors representing the words. So here we have to pad to the max length for the purposes of the experiment. We prepare the data sets. Essentially, all we're doing is just doing some preliminary actuarial work, essentially, to get our train, validation, and test X's and Y's. So we have our window of size 100, which is the maximum length here, just for the purposes of the experiment, and so on. So here, here's our vocabulary size. So this is also outside of the scope of this class. Like, this is more of a natural language processing problem. But here I'm basically looking through all of my training data, and I'm getting all of the token IDs that I can have, and like every word will be represented by a number, essentially. I'm just looking at all those numbers and counting them, and then just for the purposes of knowing what I'm dealing with, I have about 96,000 words in my training data set of 20,000 pseudo small document snippets. So we're going to use RNNs again. Here we're going to use embeddings to turn our token IDs into vectors. So this, this is a bit complicated, but yeah, when you're doing work with text or other representations, even from images, representations from CNNs, which I alluded to earlier, you have to get the embeddings first. So I'm going to run over this a little quickly now because it's not that crucial to understanding for this module. But all this is doing is that, well, given the vocabulary size, given all the possible words you can have, and given the embedding dimension, I need to have a numeric representation of how all of these words in my vocabulary map onto my embedding dimension. We talked about embeddings a lot during the representation modules of the class, like projecting information down into dimensions that mean something. We saw different ways to do that. That's kind of what we're doing here. Think of word embeddings from the very beginning. We need an embedding for every single word. And then we're going to use that as sort of a lookup dictionary for when you see an actual word sequence of pulling words from this dictionary and putting them into our input matrix. We're actually going to use a GRU. This is a gated recurrent unit. So we're getting ahead of ourselves to a large extent. A gated recurrent unit is a fancy RNN that we haven't really seen yet, but we're going to just use it for now. But you can replace this with an RNN if you want. You're going to have to do other changes here that will complicate things for you. But for now, this is just a fancy RNN. And then we have our head, which is our linear output as usual. Everything else is as normal. And again, everything's going to run on CUDA, which again can ROCm on AMDs can run that for you if you have a AMD card that can do ROCm. So this is very similar to what we've seen before also. We're going to do some training. We're going to do classification because this is a classification task, so we're using cross-entropy loss. We're going to still use the atom optimizer. What else is happening? If you're running an epoch, you either just do training or you do evaluation. You have to do either of those things. Here's where you load up the data in the device, optimization, get the model, apply the criterion for the loss function. If you're doing training at the moment, then you do backwards and you do this step. Oh, yes, right. Yeah, this could all be. This isn't coded very well, but I want this anyway. We still have, everything's as it was before. It's just spread out a little bit differently. We're still zeroing out our gradients, and after that we're producing our logits, getting our criterion, and then potentially learning. And then once we've done all of that, potentially if we're training, then we compute our loss, get our predictions, get our evaluations, and return the loss over the examples we have and the evaluation in this case, the number of correct examples we have. We do this small number of epochs, and we just report everything as usual. So let's quick glance. So I mean, you can see over the epochs, the training accuracy goes up quite a lot. The validation accuracy also goes up fairly to some extent. The training loss goes down, which is nice, and the validation loss goes down. It's hard to look at as a bunch of numbers here and get a visceral feeling of what's going on, so we plot it as usual. And we get a couple of things now. So we can look at the training accuracy. So the accuracy goes to about 100% on the training data. Now the validation accuracy starts a little bit below 80%, and it ends up somewhere around 85%. Which is still a lot better than random chance. So random chance would be 25%, so we're clearly learning something. The loss, as it tells a similar story, the loss on the training continuously gets better and better and better. It drops down in a nice smooth fashion. The validation loss seems to be pretty stuck in a more or less constant plane over here. So yeah, spoiler alert, I was going to ask you this. Is this overfitting or not? Well, it kind of is. The RNN is still doing something useful, so in a lot of use cases, it would be fine. We'd still be satisfied with a accuracy of 0.8 or something like that on validation, but we still know we can do a lot better. So there's various steps that I skipped in my code over here for various purposes, one of which is just efficiency's sake for the slides. But if you're going to have time to play around with this, and I really hope you do, try to apply some of the techniques we saw in previous modules on deep neural learning to mitigate against problems of overfitting and see what you get. In summary, the rate metric will depend on the right task. So if you're doing regression on a continuous output, you'd use MSE or MAE. If you're doing sequence classification, you're doing classification, so use accuracy or F1. If you're doing language modeling, we're getting ahead of ourselves a little bit, but if you're just trying to train a model to be a good representation of language, you would use something called perplexity. Perplexity is, 2 to the power of the cross entropy, which is a whole other thing. This is not a natural language processing class, but it's an information theoretical measure of the language itself. This is how large language models are learned to a large extent, no pun intended. And then you have sequence labeling, where you have token level F1 or token level accuracy, or indeed token level MSE if you're doing a regression at every time step, which you might for say finance modeling. So tons of use cases, each with their own metrics, which we've talked about also in the past a lot. So we remember like the memory retrieval task from example 1. The validation MSE was the right signal for us, and we had a theoretical floor. If possible, finding theoretical floors would be great to do. That's a little bit beyond the scope of this course, but it's something to try to do from a principled point of view. Our validation accuracy, we can look at the confusion matrix, which I also skipped. You can see how often different categories of news snippet is misclassified as others. That would be really helpful just for the interpretation, and those would help you align with what your goals eventually are. And I'm going to fix these slides before I post them, because I'm hiding something about the training loss, which is going to tell you something about this training dynamics. I want to pause for a second and just mention the fact that I kind of feel a little bit good that like a lot of the ideas we saw earlier in this course are kind of coming up over and over again, because it helps to emphasize like what we learned already, but you'll see that like the same kind of tools will keep on coming up. You don't need a bespoke tool for CNNs and RNNs and so on. So vanilla RNNs can still fail. We still have the problem of vanishing gradients over long sequences. If you have a sequence of like hundreds of input tokens, then gradients can be a huge problem. We know to a large extent how to deal with them though, with vanishing gradients and exploding gradients. So we can do gradient clipping, we can do normalization, we can do windowing like we saw a moment ago, always important. So far we have no explicit mechanism for forgetting or focusing. So the fact that our vanilla RNN from example 1 learned to remember x sub 0 so well was a fortunate result of the way we were training this toy model. But we had no way of telling it, like, hey, you really need to remember x sub 0, right? We didn't tell it what to focus on. And sometimes what a model needs to focus on in a sequence, especially if say words, where the semantics is very rich, will change. So we're going to need a mechanism that will allow us to focus or say attend to different representations at different moments in time over the entire sequence of this unrolled recurrent neural network. So we're going to see some interesting models in M49, which won't get to the attention part of that equation yet. We're going to get there eventually, but we'll attend instead to, we'll focus more on how to explicitly learn how to, turn on and off different parts of your memory, if that makes sense. And again, this is a preview, so we'll see it in module 49. So sequence modeling comes with its own ethical risks that other models kind of didn't. So training data can propagate biases over time. So like in a feed-forward model, bias is local. An RNN can amplify biases historically. So even if an intervention was made at a particular point in time, if there was any kind of imbalance between groups earlier in that sequence, that could still be fed forward and even amplified, as we often see, through recurrence. The model, in some sense, is conditioning whatever it's outputting on a history that can be very biased. And again, the data sequences can be biased. So we're starting to use language and text. So how things are written can be a proxy for all kinds of things. So if you can do language identification, we haven't done this in this module, but if you're doing like given some text and you want to see like not only what language is it written in, but what is the first language of the writer. So it's possible that a neural network can look at a text written by someone from France, from Germany, from Ethiopia, from Iran, from Japan. All the text is English, but the way in which it's written would still give you information about the first language of the writer, right? Maybe things are like not conjugated in the same way, or maybe the order is somewhat different. Whatever the signal is, a neural network, which is very powerful, ought to be able to find it and identify what the language, the first language of the speaker was. Even if you don't need to train a model explicitly to do that, if there is a signal in terms of first language of the writer or speaker that can be useful for the neural network to do any kind of downstream training, the neural network is going to find it and latch onto it in general. And therefore, it'll learn these biases, even if it wasn't told, even if all the data is in English and there's no explicit mention of the ethnic or linguistic background of the writer, a neural network might still rediscover these differences. So, I can't emphasize that enough, but it can come up a lot in language, and I've seen it come up a lot in the kind of language that me and my wonderful research group has to deal with. And similar problems exist in privacy. So any kind of location traces, typing patterns, lots of problems can manifest in recurrent neural networks. So before you deploy a model, again, repeating myself a little bit, but look into group differences and try to see if any kind of model predictions can be predicated on any hidden information that can be used to discriminate in any way. Here are your quick checks for. Do I hide the hit? Okay, I think I can't remember what I put here. There's some hints I'm starting to put in towards the end of the semester. But here's your quick checks as usual. You'll see the slides when you get to them. Here's some references for you. As always, it's been a pleasure. See you next time.